Yeah, so hello all. Mm. We'll be doing these two problems today. One of them is unbounded knapsack. So it's a variation of knapsack problem. So I guess you must be aware of the knapsack problem, what it is. And in this unbounded knapsack, we are given n items and certain profits and their weights and a knapsack. Its capacity is W. We are told that we need to fill the knapsack with the items in such a way that we get the maximum profit. And one thing that they have told is we can take one item multiple times. So one of the things is why won't greedy solution work over here? As we can see for this example, let's start with this example. Once again, close on the PVC. Yeah. So this is our example. So these are the given constraints. They're saying n is 3. That is, we have 3 items. And the knapsack weight is 10 kgs or 10 units. The profit that we have is 5, 11, and 13. And the weights that we have are 2, 4, and 6. So one of the things that we can do over here is, yeah, so I told why won't greedy work. So what does greedy mean? Greedy means that we, at each local, let's say at each local decision, we try to make to maximize or minimize like our decisions. But one thing is, you might get stuck at local maxima, stuck at local maxima. Hence, to overcome with this, we need to actually generate all the cases that we have, like all the decisions that we can take, and hence find the local maxima or minima. So let's take this case, the case that we have here. If we paste it again, my bad. So, oh, it came here. I'll slide it down. Yeah. So as you can see over here, what one of the things that we can do is at each item, we have the option to pick or to not pick. So if we have the weights like 2, 4, and 6, at each case, this 2, we have the option to pick it or to not pick it. At this 4, we have the option to pick it or not pick it. At this 6, we have the option to pick it and not pick it. And this is what is knapsack problem. But we have unbounded knapsack. In unbounded knapsack, this problem, this element that we picked, we can pick it again, can be picked again. So if we try to find the recurrence relation, let's say we are at an index I and the weight that we require is W, and we have our uh, profit array and the weight array, profit and the weight. So this will be an instance of our function, like our function. This will it'll have all these four parameters. Now, one thing that we can always check is, let's say if we pick an ith item, what we can do is we can pick that ith item again, or what we can do, we can go to the I plus 1th item, uh, when when we picked it, when we provided, we have picked the ith item. And the other case that we have is we have the ith item, sorry, I plus 1th item, and provided we did not pick the ith item. Earlier in knapsack, we had only two things that we can do. We pick the ith item, then we can go to the ith item provided that we pick the ith item, or else we go to the ith item provided that we did not pick the ith item. But over here, we have this extra case that once you pick the ith item, you can pick that ith item again. So it can be generalized as f of I, comma weight w, comma uh, weight array and profit array. For this item, like if we are at this case, we can pick it. So if we pick it, we'll have f of I w minus weight of I and weight and profit. Similarly, if we did not pick this item, let's say if we pick this item, we go to the next one and w minus the weight of I and weight comma profit. The another case that we can have is the third one, that we did not pick the ith item and we have to find the wth item and we have the weight and profit. So at each I, these are the possibilities that I can occur with. Possibilities at each I. And this is what defines our recurrence relation. So our recurrence relation will be something like this, and the edge cases or the base cases that we'll be having. Let's say we reach somewhere where the weight that we require, like the weight that is needed, is 0. If the weight becomes 0, then you can't add any item. Since you can't add any item, that alternatively means that you return 0 profit. This is the first base case. The second base case is our I, it can go out of bounds. So yeah, it will go. If we are going, see here, since we are calling it for I plus 1, this I, it can go out of bounds. So if this I goes to, this I goes to, like, if it's greater than n minus 1, what do we do? we return 0, right? That, uh, yeah, like the list of, mm, to be honest, this will never go greater than I, like I can never, it will go till n minus 1, but then, yeah, we can do this, to be honest. Yeah, we'll do this because the list of items got exhausted and weight did not become 0. Technically, if you think of this case, this will be never happening because it's an unbounded knapsack problem. Even if it calls for I equals, so the other case that we can do is if I is n minus 1, what we do, we return the weight that is left divided by W of weight of n minus 1 and the profit of n minus 1. It's like we took this item, uh, yeah, it's something like, whatever was left, we give it to the n minus 1 item. To be honest, I'm not sure if it will still be working or not. Mm, okay, let's trace it for this test case that we have. Oh, my bad. So the relation that we'll be having is we'll be calling for f of 0 comma 10. So if we call for 0 comma 10, what we can do, we'll be having three things. First, we have to include the profit of the first item that we took 5. We picked 5. Sorry, my bad. Mm, yeah, so the three cases for this f0 comma 10 that we can have is we pick 5 and then we call for 0 comma 5. The next that we have is we pick 5 and then we call for 1 comma 5. And then we don't pick 5, we directly call for f of 1 comma 10. Now here again, we take 5 again, 5 plus 5 plus, let's take it as 5 plus f of 0 comma 0. And this will be giving uh, sorry, my bad. Here the weight should be 8. Here also the weight should be 8 because you have to reduce the weight 1 comma 8 and then here it will be 6, 0 comma 6, and then this will keep on continuing 5 plus f of 0 comma 4 dot 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 5 plus f of 0 comma 0, and then which will alternatively give us we'll give something like, let's say 2 10 by 2. We can have 5 instances and that 5 instances times 5 is 25. This will give us somewhere around 25. if we pick 25, if we pick this item 2 5 times and give us a profit of 25, or else after this f of 0 comma 8 we can have more instances that after this f of 0 comma 8 we go to 1 and then 8, sorry, 1 and then 6 and then add 5 to it, and then again for this we can have many instances. Again for this we can have many instances. So I believe this should be working, and from here we have to take the maximum, the one that will be giving us maximum. One base case that I'm very much skeptical about is this one, that if I reaches greater than n minus 1, what should we be doing? Simply return 0. Yeah, that would work. Why we simply return 0? Because if I is n minus 1, this test case will always be running, and which is equivalent to this. So yeah, let me write down the recurrence relation once again very clearly. We start with base case. The base case is if weight becomes 0, which means nothing can be added in the knapsack. Hence, 0 profit. The second thing that we have is if I becomes greater than n minus 1, we return 0, as you can't sorry, I had to pause it. Yeah, we return 0 as you can never reach here. Add I think this is clear enough for the base cases. For the recurrence relation, we have f of I comma w equals profit of I plus f of I comma w minus w of I uh, or we can have profit of I that we added the profit, but we go to the next item. Instead of picking this item again, we go to the next item, and now the weight that we go with is w of I, because we have included this item. Or the another thing that we can have is f of I plus 1 and simply w. And we have to find the maximum of all these three things. The three things that we have to find maximum of it. So this is our recurrence relation. I hope it will be clear enough to do this thing. Let's try to code it. So we have return max profit. We can return 0 comma w comma profit array and then weight array. We can have our max profit defined anti I comma anti w comma vector integer profit and vector integer weight. Yeah, once these two things are done, we write the base case. The base case is if w equals 0, return 0. If I is greater than n minus 1, return 0 or return max profit of, sorry, max profit of I comma, I guess after these three things, I comma w comma profit and weight. And I should do w minus weight of I. One more skeptical thing is if w goes less than 0, that can also be one of the cases. So can be if w is less than or equal to 0, you can do that. But sorry, we can't include this item. Yeah, it's like we can't do that item further. Sorry, I had to give it time to process it because I'm also solving these problems first time. Or max off. We'll copy these same things. So this should be weight of I. And here instead of I, we'll go to I plus 1. Weight of I. Along with this, we can also have max profit of I plus 1 comma w comma profit comma weight. Yeah, I guess this will be doing the work. Since it's a recursion code, I guess you can compile it and check if it's giving us the correct answers. I guess we might get a TLE because it's taking too much time than expected. Yeah, we might get a TLE. Or a runtime error, not a TLE, sorry, my bad. Let's refresh the website. Yeah, let's run it. Oh, that was some random shit error. Your n can be weight dot size, or even you can take as profit dot size. Okay. We did pass few test cases, but in the other ones couldn't. Okay, one thing that I'm inspecting here is, so yeah, let me explain in this case. So the one problem that might face is, let's say the weight that we are finding here is 3, but then the ith weight came as 4, came as 4. Now if we do 3 minus 4, profit of I, let's say, is P of I is 2. So if you do 2 of f of minus 1, comma, yeah, sorry, next I, comma, minus 1, comma, those things. This minus 1 will return 0. And I can't accept that fact. Because this 2, it will be messing up with the result answer. It will be adding 2 in the profit. Yeah, so one condition that I can check here. Let's clear the screen. And that if W minus weight of I is less than 0. Okay, let's do one thing. Let's define int A, comma B, comma C. We have 3 things. Let's take them as 0. Let's take A as this thing. So here we can take A as this thing and B as this thing. Yeah, B as this thing. And then C as the last thing. This thing. What do we do? Return max of A, comma B, comma C. So here what one thing that I'm avoiding is, if case will be, if we can't add a weight, an extra weight, making the knapsack greater than allowed. So this is why that if condition is there. Let's try and check if this runs. The compilation failed. Why is that? Deposit of the deposit. Oh yeah, sorry. My bad. I can't add three things here. Lol. Doesn't even pass on. Oh, sorry, my bad. That's great. Oh, yeah, now it's passing. So now since the recursion code is done, we can memorize it. That too fast. So in memorization, what we want to do is we want to just check on the cases that might repeat, and the only factors that make the function repeat or the change in things in a function are I and W. So we define a DP vector of I range, that is the n range. The range of n can be, I'm sorry, the n range, yeah, input format, output format. Oh yeah, the n range is 10 power 3, so we can take 1, and then the weight range is again 10 power 3, so we can take again 1. And we memorize it over here, dp of I comma w as this thing. And if we check over here, if dp of is not equal to 0, so clearly the profit will be greater than 1. So we can actually return I comma w. Like our dp of I comma w, if it's initialized to 0, it won't matter. Now let's submit this. Okay, so this passes the 30 test cases that we have. And yeah, even though the time complexity is not that good, I guess it's because of the DP array initialized inside. Like as a global variable, we can have the DP variable just initialized to how much ever we want in and W, and then pass it on to the functions and then memorize it as. You got that right? It's just memorization then. Now for the same thing, hmm, let's talk about how to solve it in the tabulation format. So since you can see, only three things changed. Only two things were changed. The I that you take and the W. So 2D matrix, n rows and W as columns. So let's say we have a, let's try run the above example that we had. Let's paste the image. Yeah, here it is. So n that we can have is 0, 1, and 2. The indexes. Weights that we can achieve is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Now, for the, if you want to reach, if you're reaching weight 0, let's initialize it to 0, 0, 0, 0. Like, will be initialized to 0, 0, 0, 0, 0 everywhere. Now, for the thing that we can do here is, if we have the ith item, if we pick it, we will mark the weight 2 as done. So if j percentage, this is j, this is I, j percentage w of I is divisible, we can take that. So 0 is actually divisible. So you won't say you can take that. Let's have it as 0, 0, 0, 0. You have the 0 profits if the weight is 0. Weight of the knapsack is 0. The j is 1. The w of I will be 2. 1 percentage 2 won't be 0. So it can be 0. Here it can be 1. 1 into profit of I is 5. Here again 0. If the weight is 3. And if you have only one item. Okay, yeah, sorry, my bad. So you can take the previous item, like this 1 into 5 will be always there. And this will become 2 into 5, also be 2 into 5. This will be 3 into 5, 3 into 5, and this will be 4 into 5, 4 into 5, and this will be 5 into 5. If we come over here, W of I is 4. So 1 percentage 4. It's something like we have two items. Can we achieve 1 with these two items in place? No, we can never. That will be 0. Now we have 2. Now we have 2 and 4 as our weights. Can we achieve 2 by using 1? By using 0 and 1? Yeah, we can achieve. If two item, like we pick an item two once, we can achieve it. So the profit will be 1 into 5 itself. So as you can see, the thing that we are devising here is dp of I comma j can be maximum of the j by w into profit of I or the above item. So it will be something like dp of I minus 1 comma j. So what does this case say? That the, okay, let's try run it further. For 3 again it will be 1 into 5. For 4 it will be 11. For 5 with 22. For 6 it will be okay. If you don't pick this item, so you have this. And if you pick the item, or the 5 comma j minus 1, you achieve 6. What one can do is you have 11 and 5. GP of 5 comma j minus W of 5. As you can see over here, for 6, you can pick the fourth item. And after picking the fourth item, we'll be remaining with weight 2. That thing, we can add it with here. Getting? P of 5 plus. Let's try to code it up. Yeah. So with the recurrence relation also, we can say that we took all items with P of I, or we did not pick any item, pick with P of I as profit, and searched on previous ones. And here we picked as well as searched on previous one. So let's try to code this up. Now let's have our, okay, we have our MPI upload. To be honest, we never, we shouldn't start with j equals 0. We start with j equals 1. dp of I comma j will be max of j by w into p of I, comma max of dp of I minus 1 comma j, or dp of I comma j minus w of I. So one thing that you can check here is, sorry, we can again do a comma b comma c, because this j minus w of I can actually go like negative. So let's have it here itself, dp of I comma j minus w of I, and then a as max of, sorry, a as j by w into p of I, and the other thing as b as dp of I minus 1 comma j. So here, if I is greater than 1, greater than 0, then we should be checking behind. And then dp of I comma j can be taken as max of a comma b comma c. And the return w. Let's check if it's giving us the correct answers. Oh, sorry, my bad. You have to add dp of I and w. Okay, now let's change it to p and w. Like, let it be wt. Mm, okay, yeah, wt array. Yeah, okay, it's giving a wrong answer. I don't know why. Check it. Oh, sorry, my bad. It should be w by j. Hey, 1 second. Sorry, my bad. It shouldn't be w by j. It should be j by a of I. Yeah, see, j by w of I, d of I. Okay. Mm-hmm. Let's try to construct it for this one. So our n is 2 and the weight array is 6, 12. Profit array is 4, 17. That's what, right? Okay, my bad. This is the profit array. This is the WT array. Equals to 0, 1, 0, 1, 2, 3. Now we're doing J by WT of I. J by WT of I. Yeah, so I don't know how to go through it. Yeah, we were running this one. Profit of I. So, mhm. Mm, okay. J minus WT of I will be J is 1. So this condition won't be running for those two cases. We'll be having only J by WT of I into P of I. That is 0 itself. For 2 also we'll be having 0. 3 also will be having 0. Mm-hmm. Your 0, 0. I don't know why is it coming as 12. Let's do one thing. Let's print and check it. We'll be doing our task key. Oh, uh, we are doing this thing in here. That's wrong. Let's uncomment this part. Yeah, now we are getting it correctly. Now let's run it on the sample test cases. Perfect. Now let's submit it. Perfect. Yeah, this works. If you want it more optimized, one thing that you can do is you can have a INTDP of n comma w as 0. Mm, W plus one, sorry. Yeah. So see, we get more performance. And then similarly, in these conditions, you can optimize a little more better to get the results. One more thing that you can do is to optimize the memory. See memory graph. Ours is not performing very good. Since we are requiring only the above row, we can only take O of n space and do it. We'll be discussing it in some further videos of the further dynamic programming questions. That's it for this question.